Welcome to today's video on the A-Level Further Maths syllabus. We are going to be looking at roots of unity. So if we have some complex number z, okay, it is, well, it is an root. That's going to bug me, I'm sure it will you guys too. Terrible handwriting. Is an nth root of unity if z to the n is equal to 1, and just to note, n is a natural number here. Okay, so what we're talking about here is we can consider different powers of n and find the z which satisfy this equation, and these values of z always satisfy some specific properties, and we're going to take a look at that now. And the way we can do that is with the Mars Theorem. But first what we're going to do is just look at a couple of trivial examples. So z to the 1 equals 1. Well, z is equal to 1 is the only solution to this, obviously, because z to the 1 equals 1 can just be simplified to z equals 1, because anything to the power 1 is itself. Okay, so that's an easy example, but we're going to plot that on the Argand diagram. Okay, so the point z is at this cross here, and that's at 1. Alright. Now, what this implies, z is equal to 1, or z is equal to minus 1, and that implication probably shouldn't go both ways. Anyway, so we'll plot this one on an Argand diagram. Terrible drawing. This is 1, minus 1. So again, we get our solutions. We get a point, the same point as for z1 equal to 1, and we get negative 1 here. Okay, so now we're not going to look at z to the power of 3 just yet, because that is going to also have a complex root. So instead we're going to look at how we can find these roots of unity in the general case, because for z1 and z2 finding the roots of unity are very easy because they're just real equations we're very familiar with. So, and just to note, yes, 1 and minus 1 are real numbers, but the real numbers can be considered, I guess, as a subset of the complex numbers. So it is a complex number, but with imaginary part 0. Just because I know I said z is in the complex numbers up here, right? So in general, a complex number z can be written in the form cos of let's write this out slightly differently, because I'm skipping ahead a little bit. Sorry, the pen's going a bit wild. Let's fill these back in again. Alright, so a complex number z can be written in the form of cos theta plus I sine theta. Okay. And if we have z to the n is equal to 1, well, we know 1 is equal to cos of 2 pi k plus I sine 2 pi k. And this is because, and again, k is an integer here. So this is because 2 pi k for integers, cos 2 pi k for integers k is 1, and sine 2 pi k is 0, so it's clearly equal to 1. So we know we can write z to the n if z is a root of unity in this form, okay, because this is equal to 1. Using the Mars Theorem, z is then equal to cos of 2 pi k over n plus I 2 pi k over n, okay? If you're not familiar with the Mars Theorem, be sure to check that out in the video in the card. So now this gives us a formula for finding our values of z, okay? So z's in this modulus argument form. The argument of z is 2 pi k over n, so we're given n, so by cycling through some values of k we can find all the solutions for z. Our modulus is 1, which makes sense, but if our modulus is 1, that means that our solutions, I've just realised I've got the axes here the wrong way around, imaginary and real, okay. So we take that as 1. All our solutions for z lie on this unit circle, okay? Alright, so this circle has radius 1 as well. Alright, so when we're finding our solutions, what we notice is there is always a solution, so it doesn't matter. So for all m in natural numbers, z equals 1 is a solution to z to the n equals 1, okay? So that's our first property we have. Right, next up is, again, z to the n equals 1 has n solutions. And why is this? Well, if we put in k equals 0, this gives a solution. In fact, this gives us a solution, z equals 1. Alright, you can check that. And then we put k equals 1 in. Okay, so there's our second solution. But now, if n is equal to 2, when we put k equals 2 in, well, we get 2k, no, we get 4 pi over 2, which is 2 pi, but that is the same as 0, okay? Because that's cos of 0, because the sine and cosine graphs cycle through in cycles of 2 pi, okay? And they come back to their original point every 2 pi cycles. So we have two solutions for when n is equal to 2. We have k equals 0, k equals 1. And the same applies with the same logic for every other n, okay? So if you have n equals 5, you get 5 solutions before the solutions are non-unique. You're just going back round the circle, right? Another thing to note is our 2 pi over n apart, and this is because when you move k up by 1, you're adding on 2 pi over n to this argument, okay? So that makes sense. Now using this, we're going to look at z to the 3 is equal to 1, and we're going to plot the solutions of z. So let's go sort of 3 units up to denote 1. So this is 1, 1, minus 1, minus 1, real on the x-axis this time, imaginary. So we know from rule 1 this is a solution. We also know we're looking for 3 solutions, and these have to be equally spread out, okay, across the circle. That's what this fact tells us, because when you put, we're going to have n's equal to 1, that just gives us the 2 pi solution, and then we split off into different segments. I haven't worded that very well, but you know what I mean. We're going to go around in cycles of 2 pi over n until we get back to the start, so we must have, the segments must be evenly spaced out and fill up this whole circle, okay? So to get evenly filled out segments, we have a point here and a point here. There you go. So that's that one sorted. Now we can look at z to the 4 is equal to 1. Again, this is just a very rough sketch. And this is always a solution. Now we want evenly spaced solutions, so we just go around vertices of the circle like that. Right. So hopefully this is easy enough to understand. I believe this ends our little subsection on complex numbers. You may be asked to solve equations of the form z to the n is equal to m, where m is just some real number. Probably rational, and the way you do this is with a similar idea. You just can use this sort of cycling idea using the Mars Theorem. We can also write this in terms of ease. We look at that in another video as well that I'll leave a link to at the end of this video. So yeah, that's how you can solve equations like that. It's just your r is not equal to 1 anymore, but similar ideas still hold. So the key things to remember when anyone talks about roots of unity, it's because we're talking about solutions on the unit circle of equations where the form is z to the n equals 1. Okay, so any z that satisfies that is a root of unity. It's key to remember these key properties. So z equals 1, so it's the solution. We get n solutions, and the solutions are 2 pi over n apart. And if you can remember how we sort of derive those ideas, then that is brilliant. So please be sure to subscribe to the channel for more content. If you want to revise the rest of the stuff in this complex numbers module, I encourage you to check out the previous video, perhaps on the Mars Theorem, and as mentioned, writing complex numbers in exponential form, because that can also be another way to solve these same problems. Next up is going to be back to matrices, so hopefully you'll come back for that. Hope your course is going okay. If you've got any questions about A-level further maths, please be sure to let me know down in the comments. And that's it for this video. I hope to see you in the next one.